Good morning to everyone. It's okay. Day before I gave this problem, problem number 5. So this is the matrix A. We need to find A power 50. The A power 50 is 25A square minus 24I. Yesterday we solved a similar type of problem. So for the given 3 by 3 matrix, we got A power 32. So you should use the same idea here. Okay, try to, anybody got this answer for A power 50 for this matrix?
Yes, sir.
Okay, good. Okay, now I'll go to the next section, properties of eigenvectors. So first property, eigenvector corresponding to the eigenvalue is not unique. Eigenvector corresponding to an eigenvalue is not a unique. So proof so this means for an eigenvalue we have more than one eigenvector. So let lambda be an eigenvalue of a square matrix capital A of order n. Let capital X be an eigenvector corresponding to lambda so then so we can write Ax is equal to lambda into x. So now I'm going to multiply this equation 1, multiply equation 1 by a constant c, which is not equal to 0, non-zero constant. Okay, if I multiply, you will get what? C Ax is equal to C lambda x. So C constant into the matrix A into the eigenvector capital X is equal to, again, the constant C lambda into the eigenvector. So now you can write this is A into Cx. Okay, this one you can write lambda and C are constant. I will write lambda into C capital X. So since C is non-zero and the eigenvector is also non-zero. So we have Cx is non-zero. So therefore, Cx is an eigenvector corresponding to lambda. Eigenvector Cx is an eigenvector corresponding to lambda for any non-zero constant. So hence an eigenvector is not unique for the eigenvalue lambda. Hence an eigenvector is not unique for the eigenvalue lambda. So for example, lambda equal to 2 is an eigenvalue. The corresponding eigenvector is 2, 3, minus 1. Okay. So any constant multiple of okay, can take C. Okay, is also an eigenvector for lambda equal to 2. C is a non-zero constant. So that is the content of this property. So next to property number 2, eigenvectors corresponding to different eigenvalues are linearly independent. Proof. Okay, first I will just explain what is the statement of this property. Eigenvectors corresponding to different eigenvalues. Suppose you have lambda 1, lambda 2, lambda 3. So all of them are distinct. Okay. Then the corresponding eigenvector x1, x2, x3. So they are linearly independent. I think you know what is linearly independent means. So there are, I think I proved, I gave the definition alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3 equal to 0 only if the vectors are x1, x2, x3 are linearly independent. If the linear combination is 0, only if what? Alpha 1 equal to alpha 2 equal to alpha 3 equal to what? 0. So you should recall the definition of linearly independent vectors. So now I am going to use this idea to prove this property. So proof, please write the proof. Let lambda 1, lambda 2, I'm taking two eigen values and corresponding two eigenvectors. Lambda 1, comma, lambda 2 be two different eigenvalues of capital A. Let capital X1, comma, capital X2 be the corresponding eigenvectors, be the corresponding eigenvectors okay, then you can write what? Ax1 equal to lambda 1 x1 is equation 1, and then Ax2 equal to lambda 2 x2, this is equation 2. So I need to prove x1 and x2 are linearly independent. X1 and x2 are linearly independent. So again, okay, for this I am going to first assume that, suppose alpha 1 x1 plus alpha 2 x2 is equal to 0. Okay, I need to prove alpha 1 equal to alpha 2 equal to 0. So then only x1 and x2 are linearly independent. Okay. So now I'm going to pre-multiply by the matrix A. So then we'll get A into alpha 1 x1 plus alpha 2 x2. Right hand side also A into 0, 0. Now you can write this is alpha 1 into Ax1 plus alpha 2 into Ax2 equal to 0. But we know that Ax1 is what? Lambda 1 x1, okay, and then Ax2 is lambda 2 x2. So this is alpha 1 into Ax1 is lambda 1 x1 plus alpha 2 into Ax2 is lambda 2 x2 equal to 0 by equation 1 and 2. Okay. So now I'm going to combine the constant alpha 1 lambda 1 into x1 plus alpha 2 lambda 2 into x2 is equal to 0. This is equation number 4. So now I am going to multiply equation 3 by lambda 1. Multiply equation 3 by lambda 1. Okay, we get, so lambda 1 into alpha 1 x1 plus lambda 1 into alpha 2 x2 equal to 0. Okay. So now I'm going to write this is alpha 1 into lambda 1 into x1 plus alpha 2 into lambda 1 into capital X2 equal to 0. I call this is phi. Okay, so now look at equation 4 and 5. Okay, here I am going to subtract 4 minus 5. If I subtract 4 minus 5, alpha 1 lambda 1 into x1, alpha 1 lambda 1 x1 gets cancelled. So remaining you have these two terms. Okay, so I will write in the next page equation 4 minus 5 implies, after cancelling the first term, alpha 2 lambda 2 x2 minus alpha 2 lambda 1 x1 equal to 0. Okay, I think here what is common, alpha 2 is common. Okay, and also I think
Sir, we have x2 there.
here x2. Okay, thank you Paritosh. Yeah, okay, alpha 1, not alpha. Yeah, x2 is correct. Okay, I don't know what Avantika says. Okay, I think it is the alpha 1 alpha. I think maybe she is also telling this one. Okay, so I think I need to change this one x2. Okay, so I think alpha 2 is common and x2 is also common. So I will write alpha 2 into lambda 2 minus alpha 2 into x2. Okay, so we know that okay, we know that what, since
Sir, lambda 1, sir. Lambda 2 minus
sorry
lambda 1.
lambda 1. Thank you Vitria.
Yes, sir.
Okay, yeah, since lambda 1 not equal to lambda 2, because lambda 1 lambda 2 be two different eigenvalues. So that is the reason, since lambda 1 not equal to lambda 2, this implies lambda 2 minus lambda 1 not equal to 0. Okay, and x2 is also what? Non-zero eigenvector. Okay, so consider and this is non-zero, but the product is equal to 0. So therefore alpha 2 should be 0. Similarly, we will prove, okay, alpha 1 0. Substitute alpha 2 equal to 0 in 3. Okay, well, if I substitute alpha 2 equal to 0, you will get what? Alpha 1 x1 equal to 0. And we know that x1 is not equal to 0. So from this, alpha 1 equal to 0. Okay, proof is over. So first I need to write. Okay, substitute alpha 2 equal to 0 in equation 3. Okay, so we have alpha 1 x1 equal to 0. So this implies alpha 1 equal to 0 since x1 is non-zero eigenvector. So thus we assume what? Alpha 1 x1 plus alpha 2 x2 equal to 0. From this we have alpha 1 equal to 0 and alpha 2 equal to 0. So therefore x1 and x2 are linearly Li. Okay, linearly independent eigenvectors. Li means linearly independent vectors. Okay, the proof is over. Next, I'll give some note. Note 1. If all the n eigenvalues n eigenvalues lambda 1, lambda 2, lambda n of the matrix capital A are different, then the corresponding eigenvectors capital X1, capital X2, and up to capital X, okay, are linearly independent. Linearly independent. Okay, this is note 1. So actually this is the extension of the previous result. Okay, so in the previous property, I took two eigenvalues, lambda 1, lambda 2. Okay, and I proved that the corresponding eigenvector x1, x2 are linearly independent. So you can generalize the previous property for n eigenvalues. Okay, so note number 2, eigenvectors corresponding to equal eigenvalues may be linearly independent or linearly dependent. So you should remember the second property, may be linearly independent or linearly dependent. Note number 3, an eigenvector of capital A corresponds to only one eigenvalue of A. Only one eigenvalue of capital E. So the last note, okay, well, suppose if you have 2 minus 1, 4, okay, so it can't say like this, okay, for two different eigenvalues, the eigenvector is not same, okay, so that is the meaning of the third one. An eigenvector of A corresponds to only one eigenvalue of A. Okay, so now I'll go to some more property, but I'm going to explain because otherwise it will take time. Okay, suppose if you don't understand, please tell me, I will explain once again. So there is no need to, okay, write, just listen and then maybe you can write later. The properties of eigenvalues. A square matrix A, okay, and its transpose, A transpose, have same eigenvalues. Okay, so so look at this proof. Okay, just when for just you can think about for my question. Okay, so when the two matrices have the same eigenvalues, if you give the answer for my question, the proof is over. That's why I'm asking a question.
ट्रांसपोज मैट्रिक्स है.
No, just I am asking A and B. Suppose the two matrices A and B have same eigenvalues. I want to show that. So it is enough to show that what? It has same what?
They are transposed.
Sorry? The matrix need not be same. Okay, va?
Matrix should be transposed of each other.
And the transpose can have okay, va? Suppose A, B, and the matrix you have, okay. I want to prove that the eigenvalues of A is same as eigenvalues of B. So for this, it is enough to prove what?
Characteristic
Very
equation.
good. Very good. Okay, va? Nice. Okay, va? Bhavan and Kavimani. Okay, characteristic equation of the two matrices A and B are same. So first issue, this point should strike out in your mind. So that means, okay, so characteristic equations same. I want to prove that characteristic equations same. So for this, you need to prove what?
S1, S2, S3 are same.
Okay, S1, S2, S3 are same. Okay, va? So, okay. Otherwise, determinant of the two matrix should be what? That determinant of A minus
Same.
lambda I, determinant of A minus lambda I is same as determinant of B minus lambda I, yeah? Because that is the characteristic equation. So, so I will come from the last step. Okay, va? So I want to prove the eigenvalues of A and B are same, or A and A transpose are same. For this, I need to prove what? I need to prove the characteristic equation of A and A transpose are same or identical. For this, I need to prove what? Determinant of A minus lambda I is equal to determinant of A transpose minus lambda I. So you should, if you come like this, then you can easily think of, okay. Okay, I want to prove these two are equal. Okay, for this, we know that determinant of A is same as determinant of A transpose R. Is it correct?
Yes, sir.
Yeah. So this is the idea I'm using on, okay, in the proof. Okay, now come to the property and the proof. So I think I orally told everything. Now we will come one by step by step. A square matrix A and its transpose A transpose have the same eigenvalues. Okay, so let this is the proof. Start here. Let A equal to Aij, Ij running from 1 to n. The characteristic polynomial of A is determinant of A minus lambda I. So I think you know how to write determinant of A minus lambda I. The characteristic polynomial of A transpose. Just you need to change the rows into column. Okay, suppose this row, first row is here, the first column. A11 minus lambda, A12, A11. Okay, so determinant 2, okay, this 2 can be obtained by changing rows into columns of determinant 1. Okay, so now, so using this property or this idea, the determinant of A minus lambda I is same as what? Determinant of A transpose minus lambda I. So therefore, the characteristic equation of A and A transpose are same or identical. The characteristic equation is same, then the eigenvalues are same. That's all. So proof is, you should know the proof, but using the proof, we will solve the problem. Okay. So next I will go to the next property. Already we used this property, but I am going to give the proof. That is the sum of the eigenvalues of the matrix A is equal to the sum of the principal diagonal elements. So this is the principal diagonal, that is A11, A22, A33 is principal diagonal elements. Okay, the sum of the eigenvalues of the matrix A is equal to sum of the principal diagonal elements of A. The sum of the principal diagonal elements is called trace of A. Already I used the word trace. Okay, so I will explain. Just listen here. Okay, little bit carefully. So this is the matrix A. First step, characteristic equation, and then they are expanding here. So you know how to expand the determinant A11 minus lambda. Okay, leave this column, leave this row. So remaining is what? Multiply பண்ணி சொல்லுப்பா. A22 minus lambda into what? Please, anyone of them, please tell. A33 minus lambda minus
A32
A32 into A23.
A23. Yes, sir.
Okay, so now multiply these two. A22
Into A33
minus
minus A22
lambda
lambda
into
into A22
lambda into A22 minus
minus
lambda
lambda
into
into A33
minus lambda into A33. Okay.
plus lambda square.
Yeah, plus lambda square. Okay. Minus
A32 into A23.
Yeah, I will write that one here. Okay, minus A32. Okay, A23.
Into A23.
So totally how many terms?
Five, sir.
Four. I wrote four
Five.
here.
Yes, sir.
Okay, this term I write here 5. Okay, this is what lambda into
A33, sir.
A33. Okay, A33. Okay, so now after multiplying this, look at here. Lambda square term is here. Is it correct? Lambda square. And then, okay, from these two terms, I took lambda minus lambda common. If I took minus lambda common, what is remaining? A22 plus A33. Is it correct? Okay, and then if you expand this determinant, what you will get? A22,
A32,
A33
A33 minus A32 into A23.
minus A32 into A23. I think these two elements are
Yes, sir.
they put in determinant form. Okay, so first I expanded this. Okay, so here but now I'm going to erase it because I need to use for next calculation. Okay. Okay, now next minus A12 into, leave this column, leave this row. So remaining is what? Please tell. A21 into A33 minus lambda, okay, minus A31 into what? A23. Okay, so if you do like this, what you have? A21, A33 minus, I will write this term, minus A31, A23, and then finally I'll write minus lambda into A21. Okay, so I got these three terms. Okay, now look at here. You can see this determinant. Okay, this determinant is what? A21, A33. A21, A33. Okay, minus A31, A23. Okay, so I think this determinant, these two expression gives this determinant. Okay, and then look at here, minus lambda into A21. So I think we got these two expression, minus A21 into lambda, because minus A12 is common. Minus A12 is common, that is into minus lambda into A21. This determinant is coming from these two terms. Okay, I think I explained up to this. Next, A13 into, leave this column, leave this column, leave this row. What is remaining? Suppose if you don't understand, you can, in your free time, expand and you can verify the answer. Okay, A13 into, leave this column, leave this row, A21
A21 into
A32
A32 minus A31 into A22 minus lambda. Bracket,
okay,
sir.
yeah, okay, A3, okay, A22 minus lambda.
Yes, sir.
Okay, this is A21,
A32
A32
minus A31
A31,
into
A22
A22 minus
plus
A31
lambda into
lambda square.
A31. Okay, so you can see here, I think A13 is common. Okay, so inside the bracket, you can see here A31 lambda. Okay, so this determinant, you can see here A21, A32, that is here, minus A31 are there, A31 into A22. So that is here. Okay. So I think up to this step, I explained. Okay. Now, first I will tell what is determinant of A first. Okay. Okay. First I don't tell determinant of A, and then I'll come to later. What if you multiply these two? What you will get? Minus lambda cube. So that is here. Minus lambda cube is here. Okay. And then if I multiply these two, not these two, I need lambda square. I need lambda square. So if I multiply these two, what you will get? These two. Minus of minus plus, minus of minus plus, A22 plus A33 into lambda, lambda square. Okay. Similarly, I need, I'm going to check where I have lambda square term. Lambda square term. Okay. If I multiply these two, what you will get? Lambda square. So plus A11 lambda square. So if you combine, take commonly lambda square, you'll get what? A11 plus A22 plus A33 into lambda square. So lambda square term is also over. Lambda square term is also over. So next I need to tell how the coefficient of lambda terms plus determinant of A. I will come. Okay. So I need lambda. So okay. So if I multiply these two, I will get lambda. Okay. This is lambda cube. This is lambda square. If I multiply these two, I will get lambda. Okay. If I multiply these two, I will get lambda. Okay, and then if I multiply these two, I will get lambda. Okay, so I think these are the possibility you can get lambda. Okay, lambda. Okay, okay, lambda. I think this is enough. Okay, now we will check it. So if I multiply these two, you'll get what? Please tell. A11 into, here you have minus. Please tell. What is the, you have minus, because here you have minus A11 into A22, okay, because you have minus, that's why minus, and then minus A11 into A33. So lambda is common. So that is coming here. You can check it. A11, A22. Okay, that is the first term. Minus, okay. Okay, that term is coming here. Still, I don't get this term. Okay, that is coming from, the second term is coming from here. A11, A33. Okay, so this diagonal and this diagonal will give these two. Okay, you should be a little bit careful. Okay, now I finished this part, and then minus lambda into this. So that is here directly, minus lambda A22, A23, A32, A33. So only I need to tell this diagonal, okay, this diagonal and this diagonal. So this diagonal is actually minus, minus of minus plus. This diagonal is also minus, minus of minus plus. Okay, that is, you can see here, if I multiply these two, A12 minus of minus plus, so A21 into lambda, okay, lambda is common, okay, and if I multiply these two, you'll get what? A13, A31. You can see here, A12, A21, okay, but here minus, minus of minus is what? Plus. Similarly, this diagonal, A13, A31, minus, but here have minus, minus of minus plus. So I got a coefficient of lambda. And finally, determinant of A, here I have. So determinant of A is coming from, so that is a constant. Okay, how it is come? A11 into this, minus A12 into this, plus A13 into this. That is determinant. Okay, you know what is determinant of A? A11 into what? Leave this column, leave this row. Determinant of A22, A23, A32, A33. That is here. Minus A12. Okay, minus A12. Leave this column, leave this row. Determinant of what? A21, A23, A31, A33. That is here. Plus A13 into, leave this column, leave this row. Determinant of A21, A22, A31, A32. That is here. So if I multiply this combination, I will get determinant of E. Okay. So now I'm going to multiply throughout by minus 1. So from this step to this step, you need to do some work. Okay. So I know that some of them understand, some of them still need to do some work. So now I'm going to multiply throughout by minus. So if I multiply by throughout by minus 1, plus, minus, here plus, here minus. So that is written here. Okay. So I call this is equation 1. Okay. And then, you know, actually the sum of the roots and product of the roots. Again, I'll go to the theory of equation. Okay. Sum of the roots, that is, sum of the root is nothing but here, what is the sum of the roots? Lambda 1, lambda 2, lambda 3. It is sum of the eigenvalues. Okay. Is equal to minus coefficient of, if it is lambda cube, okay, you should write minus coefficient of lambda square. If it is lambda power 4, then you should write what? Minus coefficient of lambda cube. Okay, I think you may studied, otherwise here it is written, okay, sum of the roots. SOR means sum of the roots, that is S1 equal to minus 1 whole power 1 A1 by A0. Okay, A1 is nothing but coefficient of lambda square. A0 is coefficient of lambda cube. Okay, what is the coefficient of lambda square? Coefficient of lambda square is minus of A11 plus A22 plus A33. So minus of minus plus, okay, the numerator is what? So you can write in between these two, you can write A11 plus A22 plus A33 divided by coefficient of lambda cube is 1. And then you can write trace of A. Okay. So property number 2 is over. Property 3, that is sum of the eigenvalues is equal to trace of A. Property 3 is the product of the eigenvalues is equal to determinant of A. Okay. Suppose this is a polynomial. Okay. So a polynomial of degree n. So it has the n roots, lambda 1, lambda 2, lambda n. So already I told that sum of the roots S1 equal to minus 1 whole power 1, A1 divided by A0. Similarly, product of root Sn is equal to minus 1 whole power n. Here n, here 1. Okay, into an. An is a constant term divided by coefficient of x power n, that is a0. So here, product of the roots lambda 1, lambda 2, lambda 3 is equal to minus 1 whole power n. N is here in our problem 3 because the cubic equation into an. An is nothing but constant term divided by a0. A0 is coefficient of lambda cube. So what is the constant term here? Minus determinant of A. So is equal to minus 1 whole power 3 is minus. Constant term is minus determinant of A. Okay, divided by 1. That is equal to determinant of A. Okay, that is determinant of A. So product of the eigenvalue is equal to determinant of A. So property number 3 is over. So note if determinant of A equal to 0, then A is singular matrix. That is, okay, sorry. If determinant of A equal to 0 means, okay, you know that A is what? Singular matrix. A is singular. So both of them are same. Okay. So this implies at least one of the eigenvalues are 0. At least one of the eigenvalues of A is 0. Okay. And conversely means at least one of the eigenvalue is 0 implies this way, implies determinant of A equal to 0 or A is a singular. Okay. So that is the note here, and then we will move to the next property. So the next property is if lambda 1, lambda 2, lambda n are eigenvalues of the matrix A, then k lambda 1, k lambda 2, k lambda n are eigenvalues of the matrix Ka, where k is non-zero scalar. First we will finish this one, and then I will come to subdivision 2. Okay. So in general, the proof start from here. In general, I took lambda r. Lambda r be the eigenvalues of the matrix A, and the xr be the corresponding eigenvector. By the definition, AXR equal to lambda r into capital XR. So this is equation 1. Okay, multiplying both sides of equation 1 by k. It is Ka into XR equal to k lambda r into XR. Okay, from 2 we see that k lambda r is an eigenvalue of the matrix Ka, and the corresponding eigenvector is XR. Okay, and the corresponding eigenvector is the same as that of lambda r, namely XR. For lambda r also I have the same eigenvector XR. For similarly k lambda or also I have the same eigen vector xr. So from equation 2, we see that k lambda r is an eigenvalue of k. So proof is over for the first subdivision. Second subdivision, again, lambda 1, lambda 2, lambda n are eigenvalues of the matrix A. Then lambda 1 power p, lambda 2 power p, lambda n power p are the eigenvalues of the matrix A power p, where p is a positive integer. Okay, so come to the proof, subdivision 2. Okay, I don't need this pre-multiply by both sides of equation 1. Okay, just consider a square xr. Okay, you can write, maybe consider a square xr. A square xr, I can write a into a xr. But a xr is what? Lambda r xr. That is here. From here to here, I used 1. Okay. And then from here to here, lambda r goes here because that is a constant. So lambda r into a xr. Okay. But again, a xr by equation 1 is what? Lambda r xr. Already I have lambda r. So lambda r into lambda r xr is lambda r square xr. So from this, what we conclude? A square xr equal to lambda r square xr. Similarly, what you can expect? A cube xr is same as lambda r cube xr. So similarly, a cube xr is what? Lambda r cube xr, and so on. In general, a power p xr is what? Lambda r power p xr. So from this equation, we see that lambda r power p is an eigenvalue of a power p. But and the corresponding eigenvector equal to xr, which is the same for lambda r. Okay, and then third property. Lambda 1, lambda 2, lambda n are eigenvalues of the matrix A. Then 1 by lambda 1, 1 by lambda 2, 1 by lambda n are the eigenvalues of the inverse matrix A inverse, provided lambda r is not equal to 0. That is, A is non-singular. Because A is non-singular, then only all the eigenvalues are non-zero. That is the note we discussed here. If it is a singular, at least one of the eigenvalues of A is 0. Okay. So subdivision 3, I am going to give the proof. Now, okay, here it is pre-multiply both sides of 1 is correct. Pre-multiply both sides. What is 1? A xr equal to lambda r xr. This is 1. If you pre-multiply by A inverse, okay, you will get what you will get? A inverse into A xr, right hand side, A inverse into lambda r xr. Okay, A inverse into A is identity matrix. So I into xr is xr. Lambda r is here. A inverse and the xr is here. So now A inverse xr is the left hand side. So this is equal to what? 1 by lambda r into xr. So this is equation 4. From equation 4, we see that 1 by lambda r is an eigenvalue of A inverse, which is the corresponding eigenvector equal to xr, which is the same for lambda r. Okay. So whether we have any doubt up to this, if you have, because I explained here 4 properties, already I wrote 2 properties. Okay. If you have any doubts, you can ask me. I know that next hour also you have free hour. So I try to finish 2 more properties now. If you have any doubts, I will explain. Otherwise, I will go to the next property. Okay. The next property is the eigenvalues of a real symmetric matrix are real. So what it means? So you know symmetric matrix. That is, a matrix is symmetric. A equal to A transpose. So real means all the entries of the matrix are real numbers. Okay. So, so the property says the eigenvalues of the real symmetric matrix are real. Okay, it will not complex. Okay, so for this, okay, if you want to prove something is real, okay, in the complex numbers, how you will prove? What is the idea in the complex numbers? I want to prove lambda is real, okay, or z is real. Z ன்னு சொன்னா டக்குன்னு சொல்லுவீங்க. Z is real. Then I want to prove what? Complex numbers படிச்சீங்களா? I think +1 +2. Anybody please respond? Did you study complex number or not? Okay. So otherwise I'll stop here. We will meet tomorrow.